Swayam Prabha. Digital India. Educated India.
So I'll recall what is X now. So we are decomposing any vector in W as a sum of two vectors. One is lying in the subspace W and another is lying in a subspace is perpendicular to W. And this vector X which is lying in W, how did we obtain that? We simply take the vector V and take its projection in each of the VI directions and add these projections. I get a vector in W and that is my vector X. So this X will be called projection of V inside the subspace W. Okay, yeah, and let's show that the decomposition is unique. So suppose I have another decomposition, X prime Y prime with the same property. Yeah, X prime Y prime, the same property that X and X prime are in W and Y prime are in W prime. Then I subtract and I get X minus X prime equal to Y prime minus Y. But Y prime and Y are in W perp, X and X prime are in W, but these two vectors are equal. So these two vectors are in W as well as W perp. So it is in the intersection, but we have seen that the intersection of W and W perp is 0. So therefore X minus X prime is 0, Y minus Y prime is 0, and so X is equal to X prime and Y equal to Y prime. So therefore this decomposition is uniquely determined. So we have done one very important thing here. So we were given a big vector space. We were given a big vector space, and inside this big vector space I have a subspace W. Then first we constructed W perp, so that W perp and W intersect only in the 0 vector. Yeah. Now I take some arbitrary vector in my vector space, and I projected V inside W. This projection was the sum of the projection of V in each of the mutually perpendicular directions. So I take a orthonormal basis of W and take the projection of V in each of the mutually perpendicular directions, add those projections, that is called the projection of V inside W. Okay, and then whatever is left is perpendicular to W. So V minus sum of all the projections of V in the direction of VI. This vector is perpendicular to every vector in W, and so I have decomposed any vector in the big space as a sum of two vectors. One is inside W and another is perpendicular to every vector in W. Okay, this is so this vector which I construct inside W, okay, that is called projection of V inside W, and the function which produces this vector is called the projection operator. Just like we had projection operator when W was one-dimensional subspace, now W has become a arbitrary subspace, but we have the definition of projection that I take a vector V, decompose it as a sum of two vectors, one in W and another in W perp, and then map this vector V to X, and this is called the projection of V in the subspace W. So in concrete terms, I already explained to you how to get projection of a vector inside a subspace. Yeah. So first we construct a orthonormal basis of that subspace and take a vector in the big vector space and project it in each of the mutually perpendicular unit directions which are given by this orthonormal basis of W. Add these projections, that is called the projection of V in the subspace W. Okay, and if you write the formula, you will see that it is actually a linear transformation from V to W, and it is onto. And if I operate the projection map to any vector inside W, there is no effect. Any vector inside W by the projection vector will be mapped to itself, because if I take a vector inside W, X equal to X plus 0. So this is the orthogonal projection of X. Yeah. Okay. So we have come to this important concept of orthogonal projection of a vector inside a subspace, and if I take if I subtract the projection from V, it is in the complementary space which is W perp. The map is linear. Okay. So now why we are doing this? This is for practical applications. Yeah, it is for practical applications. We want to approximate functions by simpler functions. We want to approximate a complicated function by simpler function and also control the error in this approximation. And this is done by the idea of projection. It's a geometric idea, right? It's a geometric idea of projecting a vector along other given vectors. But let us see that it leads to very interesting things about constructing a approximation of a function in terms of given functions. Okay, so how do we do that? So let us define what is called the best approximation. So take a subspace of V and take a vector. A best approximation to V by vectors in W is a vector in W, so that the distance of V from W is less equal to distance of V from any vector in W. So we are given vectors inside a smaller subspace, and I have a vector in the big space. I want to choose a vector inside the smaller subspace which is the best approximation to this vector, and best approximation is measured by distance between these two vectors. Okay, so it says that if I can find a vector W so that the distance between V and W is the smallest among the distance of V from U for every U in W, then this vector W is called the best approximation of V by vectors in W. Okay, so in practice, how we are going to do this? So we will take, say, let us say W to be a subspace spanned by, say, 1 sin x, cosine x, sine 2x, cosine 2x. Okay, you can check using the inner product defined in terms of integral that these 5 functions are linearly independent. Okay, these 5 functions are linearly independent and they form a 5-dimensional subspace inside these the function space of all continuous functions. We can fix the closed boundary interval to be 0 to 2 pi. So take all continuous functions defined on the closed boundary interval 0 to 2 pi. This becomes a inner product space with respect to the inner product defined by the product of 2 functions. This is the inner product of 2 functions. So I take a very complicated function, but I want to approximate it. I want to find the best approximation, which is a linear combination of these 5 functions: 1 sin x, cosine x, sine 2x, cosine 2x. And you can enlarge it. You can take sine 3x and cosine 3x and add to this set. So these are, you can check that these 5 functions are mutually perpendicular, and given a complicated looking function, I want to approximate, I want to find the best approximation to that function, which is a linear combination of these 5 functions. Or we can limit these 5 functions to, say, polynomials of degree at most 3. So given a very complicated function, there is a way of approximating it by a polynomial of degree at most 3. And this is the idea behind that the best approximation of to a vector V will be by vectors in W is a vector W, so that its distance of V from W is smaller than or equal to distance of V from any other vector in W. So in some sense, this W comes nearest to V as we vary vectors in W. So this W is called the best approximation. So question is, how do we obtain the best approximation? So let us see that the projection of V inside W is the best approximation of V by vectors in W. Yeah, it is the closest vector. The projection of a vector inside a vector space, subspace, is the closest vector to the given vector by vectors inside W. Okay, so let V be in V and W be a subspace. This V is a inner product space. Then the projection of V inside the W is the best approximation to V by vectors in W. So we need to check this condition. to show that the projection vector is the best approximation. Yeah. Okay. So just check the distance of v from any vector. Take any vector and look at the distance of the given vector v from w. Is square of the square of v minus w, norm of square of the norm of v minus w is norm of v minus pwv plus pwv minus w. Yeah. So I just add and subtract the projection of v inside w, and we know that these two vectors, yeah, this is a vector in w, because this is in w, this is in w, this is a vector in w, and I have proved that before, that if I subtract the projection of v in w from v, this is perpendicular to every vector in w. So this vector and this vector, they are perpendicular to each other. I can apply Pythagoras theorem and say that the square of the norm of sum of these two vectors is the square of norm of each of these vectors. So this is by Pythagoras theorem. Okay. Yeah. So this is because this is perpendicular to these two vectors, so it is perpendicular to the difference. But this is bigger than or equal to 0, and therefore the square of norm of v minus w is bigger or equal to square of norm of v minus pwv. Yeah. So distance of the projection of v, so this w is any vector, okay, in v. So distance of v from w is bigger or equal to distance of v from the projection of v in w. So in this sense, the projection of v in w comes closest to v if you vary vectors inside w, and so therefore this is the best approximation. Yeah. Suppose I have another best approximation, then I'll show that u has to be equal to the projection of v in w. So u is any other approximation, best approximation. That means the square of norm of v minus u. I add and subtract the projection, and then by Pythagoras theorem it is equal to this. Yeah, this is bigger or equal to v minus the projection of v inside w norm square, right? But u is a best approximation to v. Yeah. So that means distance of v from u is less or equal to distance of v from any other vector in w, and therefore this is also true, because u is a best approximation. U is another best approximation to v. Okay. So this is bigger or equal to this, and so therefore equality must hold everywhere, and therefore this must be equal to 0. Yeah. And this implies by positive definite property that u must be the projection of v in w. Okay. So there is a unique best approximation. Yeah. There is a unique best approximation of a vector inside a given vector subspace of an inner product space, and that best approximation is the projection of that vector inside the subspace w. Okay. Okay, now we want to apply this idea, okay, to construct best approximation of a vector in the column space of a matrix. Okay, so suppose we Rn, consider Rn with standard inner product, dot product, okay, dot product of vectors, and take a matrix n by m matrix where m is less equal to n. So the number of columns, number of rows is number of columns is smaller than number of rows, so it's a tall matrix. Yeah, number of columns is smaller than number of rows. So take a tall matrix. Yeah, take a tall matrix, and this is a n by m matrix. Okay, so the vectors, the column vectors of A, there are m column vectors. They are all inside Rn. Okay, column vectors of this matrix, they are inside Rn. Okay, and we want to find a best approximation of a vector in Rn which is inside the column space. Yeah, that's our problem. So we have solved this problem by the idea of projection. Okay, so I have the matrix, and I have these column vectors of the matrix, and the column vectors of the matrix, they are living inside Rn. Okay, all these vectors are living inside Rn, and I want to find a linear combination of these, that is a vector in the column space which comes closest to a given vector in Rn. And by the theory that we have developed, it says that this vector, the vector which comes closest to V, which is inside the column space of the matrix, is the projection of V in the column space of the matrix. So how are we going to find this? Well, take the column space of the matrix, yeah, and then construct a orthonormal basis of the column space, and then take the projection of V by fixing this orthonormal basis in the column space. That is the best approximation in the column space. Yeah. So we want to now derive a formula for the best approximation of V inside the column space without going through the Gram-Schmidt process. Okay. Gram-Schmidt process requires you to go through a whole sequence of operations which will produce a orthonormal basis. But let us show that we can actually bypass this process and still find the best approximation of a given vector in the column space of a given matrix. Now we have a tall matrix. Yeah, we have a tall matrix. The number of rows is much more than number of columns. Okay, and in applications usually we come across tall matrices, and many problems in applications reduce to finding the best vector in the column space which is closest to a given vector in Rn. Okay, so let's do that. So we know that if we are given an arbitrary vector in Rn, then the projection of this vector B in the column space is the best approximation of B in the column space. Yeah, but vectors in the column space, they are of this form. Linear combinations of column vectors of A is simply Ax. Yeah, this we have seen this before. Ax is simply x1 a1 plus x2 a2, etc. There are m column vectors, so xm am. Okay, so we are trying to find a vector in the column space. A vector in the column space is a linear combination of column vectors, but I can write this as Ax. So this vector Ax, okay, it is going to be a projection of B. It is going to be a projection of B. But once I subtract this projection from B, the remaining vector is going to be perpendicular to the column space. Yeah, that is how we found the properties of the projection. So if we take a arbitrary vector and take the difference of this vector from the projected vector, then this difference is perpendicular to every vector in the subspace. Yeah, so this vector in the column space is orthogonal projection of B in the column space, and if and only B minus Ax is orthogonal to every column of A. When I subtract this projected vector, which is best approximation, then I get a vector. This vector is going to be perpendicular to every column of A, so it is going to be in B minus Ax will be in CA perpendicular. Okay, so B minus Ax is perpendicular to every column. But when I take transpose of the matrix, then the row vectors are the column vectors of A. Row vectors of A transpose are column vectors of A. To say that B minus Ax is perpendicular to every column vector is to say that A transpose times B minus Ax is 0. B minus Ax is a vector. A transpose B minus Ax is simply the components are going to be take row vectors of A transpose and take dot product with B minus Ax. But the row vectors of A transpose are column vectors of A. We want B minus Ax to be perpendicular to every column vector Okay, so therefore A transpose B minus AX is 0. So simplify this. It says A transpose AX is equal to A transpose B. Okay, so if AX is in the column space, which is the best approximation to B, then AX has to satisfy this equation that A transpose AX is A transpose B. Right? These are very important equations. These are called normal equations. So we wanted to find best approximation of B in the column space of a matrix. Yeah, then it says that this is going to be AX, and AX is a solution of this inhomogeneous system of linear equations. A transpose AX equal to A transpose B is a system of linear equations. Yeah, so now we have to solve this system of linear equations. So let's do that. We have to show that this system of linear equation always has a solution, and many times it has a unique solution. X will be uniquely determined, and so AX will be the best approximation of B in the column space. But we want to show that these normal equations always have a solution. So if X is a solution of these normal equations, then AX is the projection of B in the column space. So our problem is to find best approximation of a given vector inside a subspace. Yeah. So if my subspace is consisting of some usual vectors in Rn, okay, then I can make a matrix. I can make a matrix out of this subspace. Simply take a basis of that subspace, and so those basis vectors, make them as column vectors of a matrix. So to find the best approximation of a given vector inside the subspace, it is same as finding the best approximation of the given vector in the column space. To find the best approximation in the column space, we derive the normal equations. And now we want to show that the normal equations always have a solution. Okay, and we know this by using Gramscian process and projection, etc. We know that there is a best approximation, but we are now approaching the same problem from a different angle. We will show that the normal equations have a solution, always have a solution. Once you have the solution, then AX is the best approximation to B. Okay, so to do this, let us first prove that the rank of the given matrix, this is a tall matrix, is rank of A transpose A, and it is also equal to rank of A transpose. Yeah, so A is arbitrary matrix with real entries, and I'm proving that the rank of A transpose A is same as rank of A transpose is equal to rank of A. So instead we will prove that their null spaces are equal. Yeah, null spaces of these two matrices A transpose A and A are equal, and so the dimension of null space are nullity of these two matrices, and once the nullities of two matrices which has same number of columns are equal, the ranks are also equal by rank nullity theorem, because the rank of a matrix and its nullity, they add up to number of columns. Number of columns of A is n by n matrix, there are m columns, and A transpose A is an m by n matrix. Okay, so if I prove that null space of A transpose A is same as null space of A, I would have proved that the nullity of A transpose A is same as nullity of A, and so but the rank of A transpose A is m minus the nullity of A transpose A, and the rank of A is m minus the nullity of A, but these two nullities are same, and therefore their ranks will be same. Okay, so using the rank nullity theorem, now it is enough to prove that the null space of A transpose A and null space of A, they are equal. Okay, so just prove that each null space is contained in another null space. So pick a vector in the null space of A. So that is AU equal to 0. If U is in the null space of A, AU equal to 0, and therefore A transpose AU is also 0, and therefore U belongs to the null space of A transpose A. So null space of A is always contained in null space of A transpose A. We want to prove the other containment, that the null space of A transpose A is contained in null space of A transpose A. Yeah, pick a vector in the null space of A transpose A, and yeah, then A transpose AZ is 0 because I picked a vector in the null space of A transpose A. I want to show that this Z is in the null space of A. Okay, this Z is in the null space of A. So look at this vector AZ. AZ is in the column space. AZ is in the column space of A, and A transpose AZ is 0 means AZ is perpendicular to every row vector of A, because the row vectors, the A transpose times AZ equal to 0 means AZ is perpendicular to every row vector of A, but the row vectors of A transpose are the column vectors of A, and so therefore this AZ is in the column space of A. It is perpendicular to all the columns of A, and therefore it is in the perpendicular subspace of column space. But we have proved that W intersection W perp is only the 0 vector. So AZ is 0. So therefore W is 0. So therefore so if W is 0, AZ is 0, and therefore Z is in the null space, and therefore null space of A, and A contains the null space of A transpose A. So these two null spaces are equal, and therefore the nullities are equal. So nullity of A is nullity of A transpose A. Now you substitute A by A transpose. We know that nullity, the rank of A transpose and rank of A they are same. Yeah. So this also shows that rank of A transpose A is rank of A, and rank of A is rank of A transpose, simply by substituting A by A transpose and using the fact that A and A transpose have same rank. Okay. So we have proved here that the rank of A is rank of A transpose. It is also rank of A transpose A. Okay. Yeah. A transpose is a nice matrix. It is symmetric. A transpose A is also a symmetric matrix. So starting with a very random matrix, we have produced another matrix which is symmetric. Yeah. And its rank is the same as the rank of A. Okay. This we will see later. This idea is very useful. Okay. So let us see as a consequence of this that A transpose A, which is M by M matrix, is invertible if and only if columns of A are linearly independent. So A was a tall matrix, right? A was a tall matrix, N by M. Okay, it has M columns. So this says that if the column vectors of A are, the rank of A cannot be bigger than the number of columns, because number of columns is smaller than or equal to number of rows. So column rank is the rank of the matrix, and if the columns are linearly independent, then A transpose A, which is a square matrix, will be invertible if and only if. Okay, this is a simple application of this fact that rank of A is rank of A transpose. So if A transpose A is invertible, it's an M by M matrix. Yeah. So this is an invertible matrix. So its rank is M, but rank of A is rank of A transpose A. So rank of A is also M. So if a matrix has M columns and its rank is also M, then those M column vectors are linearly independent, and vice versa. Okay. So A transpose A is invertible if and only if columns of A are linearly independent. Yeah. So but if the columns of A are linearly independent, then this A transpose A is invertible. Our normal equations were these: A transpose AX equal to A transpose B. To find the best approximation of B in the column space of A, which is AX, we have to solve this normal equations: A transpose AX equal to A transpose B. But if columns of A are linearly independent, A transpose A turned out to be invertible. So I can multiply by the inverse on both the sides and solve for X. X is inverse of A transpose A times A transpose B. So X is uniquely determined, and AX is the projection of B in column space of A. Okay. So normal equations can be solved. There is a unique solution when columns of A are linearly independent. Yeah. Now columns of A, but if columns of A need not be linearly independent. Yeah. Need not be, columns of A are linearly, then the solution of normal equation is unique. But otherwise also there is always a solution. The normal equations A transpose AX equal to A transpose B have a solution in any situation, even if the column vectors are not linearly independent. Okay, let us see why that is so. Yeah, so look at the rank of A transpose A. Okay, I join the vector A transpose B. We are trying to solve the normal equations. So to solve normal equations, we construct the augmented matrix. This is the coefficient matrix A transpose A. I construct this augmented matrix. So when I add these additional column vectors, of course the rank may increase. Yeah, it will not decrease. Okay, so rank of A transpose A is at most the rank of A transpose A transpose B. This augmented matrix. Yeah, but this augmented matrix is A transpose times A transpose B. Okay, so this is rank of A transpose times this, but when I multiply a matrix on the right, okay, the rank satisfies this condition. Rank of AB is less than equal to rank of A. Okay, use linear transformations to see this fact that rank of AB is less equal to rank of A. So rank of A transpose times this augmented matrix is less than equal to rank of A transpose, but rank of A transpose is rank of A transpose A. Okay, so therefore this number is equal to this, and therefore we should have equality everywhere. Okay, so the rank of A transpose A is same as rank of A transpose A transpose B augmented matrix. Once the augmented matrix and the given matrix have same rank, if rank of A is same as rank of augmented matrix, this means B is in the column space. Yeah, B is in the column space. B is linearly dependent on the column vectors of A. Once B is in the column space, B equal to some x1 A1 plus x m AM, and therefore this is equal to AX. So there is a solution. There is a solution of the normal equations. So normal equations will always have a solution. And once I find this solution by Gauss elimination method or some other method, then X is the solution, X is a solution, and then operate A on X, and you will find the best approximation of B in the column space of A. Okay, what is the use of these things? So this is the use to do data fitting. Yeah, when we are presented with a lot of data, we want to draw some conclusions. Yeah, sometimes the data will lie on a straight line, so there will be very simple relations among the data. Okay, sometimes the data will lie on a curve like a parabola or hyperbola. So given the huge amount of data, we want to draw some conclusions, and this is a big branch called data science, and this is a very humble introduction to data science. This is called least square approximation. Okay, least square approximation. So data fitting ultimately is derived from the idea of projection. The idea of projecting a vector in a subspace gives us the best vector in that subspace, and this idea has numerous applications. So I will show you two applications of this idea to data fitting. So data fitting is done by many methods. Least square approximation is one of the favorite methods. Okay, yeah. So suppose that we have a large number of data points xi, yi. Okay, and they are collected from some experiment. So plot these data points in the plane. They have two coordinates. Yeah, once you plot, many times you will see that they are actually clustering around a straight line. Okay, visually you can see once you plot this data that there may be a straight line which fits the data. It will not pass through all data points. Okay, but most of the data points will lie on a straight line, but there may be many straight lines, yeah, which will pass through these data points. We want to pick the best straight line. That means the line which in a sense which I will derive accurately, that the errors will be minimized. Okay, you want to pick we want to pick a straight line which best fits the data. So how do we do that? So suppose we have large number of data points xi, yi, and they are collected from some experiment. Okay. Sometimes we believe that these data points lie on a straight line. Yeah. So we want to fix a straight line whose equation is s plus tx, and this straight line may satisfy yxi equal to yi. Some of the data will lie on the straight line, some may be away from this straight line. So if all the data satisfy this equation, then of course we have found a straight line, but they may not. Okay, they may not. But always there are some experimental errors, and so these data may not be exactly lying on a straight line. Yeah. So in practice, these points will deviate from the straight line, and it's impossible to find a linear y-axis that passes through all of them. So we want to find the best straight line which passes through these points. Best in the sense that the errors are made as small as possible. When we fit this straight line, the errors from the actual data are minimized. So a natural question that arises now, how do we define the error? Okay. So consider the following system of linear equations in variables s and t, and the known data points xi, yi. Then look at these equations. So if my straight line exactly fit all the data points, all these equations will be satisfied, and then I am satisfied, and this is the line. Okay. But it may not be the case when I substitute the input measurement xi. I may not get the output. Okay. But I want to measure the difference between this actual value which is predicted by the equation of the straight line with the experimental value y1. So I want to minimize the difference. But the differences could be in either direction. They could be positive or negative, right? So we want to have a method of computing the error in a nice way. Okay, in a nice way. So the errors, we can take the experimental value yi and the predicted value s minus xit, and take the difference and take the absolute value, and we can add these things. This is the sum of the errors. Yeah, but the errors can be constructed like this, that it is yi minus s xit absolute value and add all these errors, or we can take the square of the difference. Yi is the experimental value, and s minus xit is predicted by the straight line model, and I take the difference of the actual value with the predicted value, square this, and add all these squares and take the square root. This is called least square approximation method. This is also a valid method. We could take the max of the deviations from the experimental value and the predicted value. Call this also as an error. Okay. So you fix your definition of error, and then we can get the right fit. Okay. So there's a theory for each types of error, but in practice, the least square approximation is preferred. Okay. So we want to find the parameters of the straight line so that this error is minimized. That is the data fitting problem. Find a straight line so that these errors, the sum of squares of these errors and their square root, it is minimized. Okay. So this is a maximize minimize problem. There are two parameters s and t. Of course, you can say, all right, this is a nice equation. I want to minimize the error. Take the partial derivative with respect to s and t, and then use maximize minimize criteria and find s and t. But let us now show that there is a linear algebra method which will actually find the s and t so that these errors are minimized. And so to minimize the error, find the straight line so that these errors are minimized. That is called the least square problem. Okay, that is called the least square problem. So I will continue with this because I think our class time is over, and next time I will show applications of these ideas of best approximation, projection of a vector in a subspace, then how to solve normal equations to data fitting problem. So I will take two examples. One is given a huge amount of data, and suppose you suspect that there is a linear relation among them, how to find the best straight line which fits the data. Sometimes the data may fit on a parabola, okay, For example, if a projectile is there, I take observations at a few time intervals, measure the height of the projectile, I can find the equation of the parabola. Okay, this has many interesting applications in celestial mechanics, and that's where the method of least square approximation was first invented by Gauss. So I will illustrate the least square approximation by fitting a straight line and fitting a parabola to a given set of data points.